The next question, the major product formed in the following reaction sequence is, so this is an aryl allyl ether which has one CHO group at ortho position, which is treated with a phosphorus halide. So the first reaction will be a reaction between this CHO group and the phosphorus halide to form an alkene. So we'll draw the first product. This will be the first product. Now you may have one doubt that I am drawing this at a cis configuration, but this is a stabilized halide, so trans product will be the major product. But if we see the options, then all these cases will have the cis configuration. So the reaction must be kinetically controlled and the product is cis. So after that, when it is heated with 200 degrees centigrade, then a 3,3 sigmatropic rearrangement will take place, that is Claisen rearrangement. Aryl allyl ether will undergo Claisen rearrangement, and this group 3,3 sigmatropic rearrangement, that is 1 2 3 1 2 3. So the product will be, this group will migrate at ortho position, one, two, three, and OME group will be at meta position. It will be OH, and this will be hydrolyzed. This ester will be hydrolyzed to another ester, that means OH lone pair will attack here, and the OET group will be removed as ETOH. So a cyclization will take place, and also this is an again aryl allyl ether. So again there is a 3,3 sigmatropic rearrangement, that is a cope rearrangement. So this is 1 2 3, this is 1 2 3. So this group will migrate here at position 3. The product will be here cyclization will take place. So a 6-member ring will be formed. Six-member ester will be formed, and the OME will be as usual here, and this group will come into para position 1 2 3. The double bond will be here, and 2-methyl group will be in this position, and here aromatization will take place. So the product will be this. If we see about the options, this is the product. If we see about the options, this is the product. So guys, if you have any doubt regarding this video, please let me know in comment box. Next question, the correct order of Hammett reaction constant rho for the deprotonation of the following carboxylic acid. So all these are carboxylic acid. So what is rho? The Hammett reaction constant. Hammett reaction constant, you can say it is the susceptibility of a particular reaction. Again I am telling that it is the susceptibility of a particular reaction towards the substituent. That means here the every reactions will have a different rho value. Here 3 reactions are involving, and all these reactions are the deprotonation of carboxylic acid. So for these 3 reactions the rho value will be different. Now as you can see here that deprotonation will happen in this OH. So as the reaction center will go far from this substituent, the effectiveness of this, the polar effectiveness of this substituent will be different on that reaction center. Again I am telling that if the reaction center goes far from this substituent, here the reaction center is separated, nearer to this substituent, but it is separated by one carbon atom, CH2 group here, and it is separated by 2 CH2 group in C. So as the reaction site goes far away from the substituent, its polar effectiveness will decrease, and consequently the rho value will decrease. And you have to remember here that rho will have positive value if the reaction center develops a negative charge, and rho will have negative value if the reaction center will develop a positive charge. So here all these things, when the OH group will depart, the carboxylate anion will be formed, that is the reaction center will develop a negative charge, that means rho will have positive value, and it will have the highest rho value, and then will have B and then C. So the order will be A greater than B greater than C. This is the correct option. The next question, the correct statement for the following transformation. So this reaction is a name reaction, is a Friedlander-Quinoline synthesis. So here two conditions are given, A and B. A is aqueous KOH ETOH at 0 degree centigrade, that means it is kinetic controlled, kinetic controlled condition, while condition B, which is in refluxing condition, so this is the thermodynamic condition. Now under here what will happen here, two molecule of H2O will be removed, this H2O, and here two hydrogens are there, these two hydrogen and oxygen will be removed as H2O. So two molecule of H2O will be removed and quinoline will be formed. Now here two options are there. Now this alpha H2O can be removed, or here also two hydrogens, these two hydrogen can be removed. Now we have to determine that in which condition what hydrogen will be removed. Now if we see, as we know that under thermodynamic condition the reaction will go from by more stable enol formation. Now under thermodynamic condition this is the more stable enol, and another enol can be formed from this side. This is this enol. So this is more stable because this is more substituted enol. So under thermodynamic condition this enol will attack to this carbon center. So that means this carbon will attack into this carbon, and from this attack we will get the product Q. Finally we will get the product Q. Now under kinetic condition, as the base employed is a small one, it will preferentially abstract photon from the less entered side, because here as one methyl group is present, so this photon is sterically more hindered than this photon. So OH minus will preferentially abstract this photon, and the enolate will form this enolate, and it will attack into this carbon. So this under kinetic control, this carbon will attack at this carbon center, and from that we'll get the product P. So Q will be formed under thermodynamic control and P will be formed from kinetic control. So Q is preferentially formed via condition B, that is under thermodynamic control. This is the correct answer. So guys, if you have any doubt regarding this video, please let me know in comment box.